Hi guys, thanks for tuning in to my video on strong and weak acids and bases. Hope you enjoy it, and let's get started. If we were to compare acetic acid and hydrochloric or nitric acid as they're having a reaction with metal, what we'd find is that acetic acid doesn't react fully with the metal that it gets in contact with, whereas hydrochloric acid and nitric acid, it does react fully. And the reason for it is basically just because hydrochloric acid and nitric acid, they are strong acids. Acetic acid is known to be weak. The difference is the degree of ionization. So for example, as we've seen before, hydrochloric acid, put it together in water, and what we get is we get a full ionization of the hydrochloric acid molecule. So we get some hydrogen ions and we get some chlorine ions in with the water, and eventually they may the hydrogen may combine with the water to create a hydronium ion. Same thing goes with nitric acid, HNO3. Put it into water and you'll get some hydrogen ions and you'll get some nitrate ions in the water. But if you compare that with acetic acid, which is CH3COOH, put that together with water. Now I'm going to use a new symbol here. It's going to partially react, and you'll end up with it's a single hydrogen plus the acetate ion, so it's CH3 plus water. And so what this symbol here means is that some of the acetic acid is moving forward and ionizing, and at the same time some of those ions are moving back into acetic acid form, and so the reaction goes backwards and forwards and backwards and forwards again until it reaches what's called an equilibrium situation. And in that equilibrium situation, basically we'll have some acetic acid molecule like so, and then we'll have some ions. And so it's left just basically partially dissolved, and the acid isn't strong as a result. So about 1% of the molecules ionize in weak acids like acetic acid, whereas strong acids will ionize completely. Hydrochloric acid ionizes completely. 100% of it goes into hydrogen ions and chlorine ions. Most acids are actually weak, but I just gave you an example of some strong ones there. Acids with one hydrogen in the formula, like hydrochloric, hydrobromic, nitric, hydroiodic, for example, are typically strong. However, hydrofluoric is a weak acid. Can you imagine why that would be? Just remember that we're talking about, okay, so hydrofluoric AQ, put that together with water. What we're saying is it's a weak acid. In other words, it's hard for it to go like this, for it to break into hydrogen and fluorine. And as you can imagine, because fluorine, as we've talked about before, has such a high electronegativity, it's one of the most reactive elements in the periodic table. It's got a very strong bond with the hydrogen, so this forward reaction isn't going to happen very much at all. It's going to prefer to stay this way. It's going to prefer to stay in the bonded state where the hydrogen is right there together with the fluorine. Okay, so this reaction, the forward reaction, won't go on very much. So there'll be a very small percentage that's actually ionized. So what about acids with more than one hydrogen in their formula? Well, there are names for these. So acids with a single proton are called monoprotic acids. Acids with two hydrogens are called diprotic acids, and acids with three hydrogens are called triprotic. acids. Okay, so for example, here we have sulfuric acid. That's an example of a diprotic acid. Hydrochloric acid, that's an example of a monoprotic acid. Phosphoric acid, that's another example of a triprotic acid. Okay, and in the case of these acids, which have maybe 2 hydrogens or 3 hydrogens, it's going to have an effect on the dissociation, those number of hydrogens. So for example, sulfuric acid here, H2SO4. First thing, when it gets together with water, that it will do is it's going to try to get rid of at least 1 hydrogen. So the first step we'll take is to go ahead and release 1 hydrogen ion, and then we'll be left with HSO4, okay, with a -1 charge. Okay. And then the next step would be for that HSO4 to go ahead and attempt to release the other hydrogen. So it's kind of like a 2-step process here. So again, we've got a hydrogen, and now we're just left with the sulfate ion. So now this is 2 negative. Okay, the thing is, this first reaction is going to be a lot easier to take place than this second reaction, because we've already, okay, I should have had a negative in there, because at this stage we've already got a negatively charged HSO4, and then we're trying to take another hydrogen ion away from it, and it's already negatively charged. It would resist trying to take more positive items out of that particle. So this is going to be a difficult reaction to happen. Gets even worse with phosphoric acid. So here we have H3PO4. Put that together with water, and the first reaction will be to take away 1 hydrogen. Okay, then we're left with H2PO4. And then the next step, we take that H2PO4 with a -2 charge, so H2PO4, now it's got a -2 charge. Oh, sorry, -1 charge, because we've released 1 hydrogen. Okay, put it in some more water, or it's in water already. Release another hydrogen, and we're left with HPO4 with now a -2 charge, and then plus water. Third stage, and the most difficult stage, the least likely stage to actually take place, would be to break down this HPO4 particle, HPO4 with a -2 charge. Once it gets into water, it's going to turn into another, again, hydrogen ion plus just the phosphate ion. Okay, so it's a 3-step process here. This one will take place fairly easily. This one will be less easy. And then this third one will be difficult, because these things are becoming more and more negative, and so why would they want to get rid of more positive charge within themselves if they're already a bit negative, right? So that's how that works. So this would be a strong reaction. Reaction 1 would be a fairly strong reaction. 2 would be less strong. 3 would be kind of a weak acid type of situation. It wouldn't go fully to the right. In fact, we would write in one of these symbols. It's an equilibrium type of situation. It's not going fully forward. This one may also be kind of an equilibrium situation, the first one is more than likely it will go forward fully. Okay, so we define bases the same way. If they're strong, they'll be fully ionized. If they're weak, they won't be fully ionized. It's measured by the degree of, dissociation, not ionization. We call it dissociation because we're not actually making ions. Bases are already ions. They're just separating from each other. And so the strong bases are going to be the oxides and hydroxides of alkali metals. So for example, sodium hydroxide or sodium oxide, those would be example of strong bases, okay, when you add them to water. Oxides and hydroxides of group 2 metals as well. So for example, magnesium hydroxide or MgO, magnesium oxides. Those would be examples of strong bases. Anything else isn't likely to be so strong. And just what we find is with sodium hydroxide, add it to water, and you're likely to get full dissociation. So you have your sodium plus you'll have your hydroxide formed as a result. Okay, sodium oxide plus water will form sodium hydroxide, 2 of them in aqueous form. So really it's like that. So there's 2 sodiums. With the 2 sodiums, 2 oxygens there, 2 oxygens, 2 hydrogens, 2 hydrogens, and so that all balances out. Okay, so those are example of strong bases. We know they're strong bases because they will fully dissociate. This forward reaction will happen fully. If it didn't, then we would use this in the equation just to show that it's an equilibrium type of a situation. We're getting some forward reaction happening, but we're also getting some backward reaction happening, and the molecule in question isn't dissociating fully. Okay, most bases are weak. So the most common weak base, we've talked about this one, is ammonia. So 1% of it dissociates in water. In other words, you remember that's ammonia. Okay, it comes as a gaseous form, gets together with water, and we end up with a little bit of a forward reaction, but a little bit of a backward reaction as well. What ends up happening is we get ammonium ion, and we're also left with some hydroxide, the leftovers from this water molecule which has been pulled apart. So this only happens about 1%. So 1% of the ammonia molecules change into ammonia ion, and the rest of it stays on the left side of the equation here.